Let's start the notebook called Simple Qubit Operation using Qiskit. To use this notebook, you will need to have Qiskit installed. If you don't have it installed, you can go to your terminal and type pip install Qiskit, and it will download and install it to your computer. Then when you execute this cell, it should produce something like this to tell you which version you are using. At the moment, this should be the latest version. Then we will import the necessary objects from the Qiskit library to implement our circuit. So in this third cell, we begin to set up the circuits by specifying how many quantum registers, aka how many qubits that we need, and also how many classical registers that we will need. So in our case, we will be working with 2 qubits and 2 classical registers. Then you combine these things to have a quantum circuit, and this object will be our circuit that we will do operations on. So let's start with a very basic example and apply the NOT gate, the X gate, to the first qubit. Then measure this circuit. So if you want to draw this circuit and have a look at how does it look, it looks something like this. We applied the NOT gate to the first qubit, and we have 2 measurements that we apply on both qubits. Our circuit is ready to be executed. Until this part, we only set up the circuit. Now we need to execute it. So you can execute it using this Chasm simulator backend. We will talk about this backend in more detail in a future notebook. And we will be using shots equals to 1 for now, which will be the amount of measurements that we will do on this quantum circuit. Then you can get the results with this line of code and print what you got. In this counts dictionary, you will have the measurements and how many times that you measured that specific state. So in our case, we are expecting only 1 measurement since we chose shots equals to 1. In this case, we got 0, 1, which we were expecting since we applied a NOT gate here. In Qiskit, states start from 0. Both are 0 at the beginning. We apply 1 to this, and this state becomes 1, and this one stays same, stays at 0. Very simple example. This time we will be using a single qubit and a single classical register. We set up our circuit as we did above, but we select 1 here and 1 here. This time we apply a Hadamard gate to our quantum register. Then if we draw it, it looks like this. And after the Hadamard, we are measuring it. This time we will be executing the circuit 100 times and observe the outcomes. As you see here, when we print the counts, we observed 0 state 51 times and the 1 state 49 times. From the theory, we expect to have 50-50 division between these states. So if we just have a look at here, the plus state is like this, and the probabilities are square of 1 over square root 2, making 0.5 and 0.5. But since this is a finite measurement, we don't always get direct division, direct ratio between states. We will talk about this in more detail in future notebooks, but the important thing here is that we got something very close to that what we expect. So let's try another gate. In this case, we will be using the RY gate, and we choose the theta, the rotation angle, to be pi over 3, making 60 degrees. We will take the 0 state and rotate it by 60 degrees. So in this case, we obtain this state. And if we have a look at the probabilities, the probability of getting 0 states is now 0.75, and getting the 1 state is 0.25. So let's implement our circuit. We again use just a qubit. We import a math library to use the pi from there, and we apply the RY gate to our quantum register with this pi over 3 parameter. Then this time we choose shots to be 1000 and execute our circuit. We can also show the counts using the visualization tool of Qiskit with this import. And you see here that what we got, the result we got from this measurement. So here we have 0 with probability 0.787 and 1 with 0.213. So this is very close to what we expect from theory, but again, this is due to us having finite shots, and as we increase this number of shots, we will get much closer to this ratio, and we will also talk about effects, these kind of effects, in the next notebook.